Hey everyone, welcome back. We are starting some applications of the derivative, and we're going to start specifically how it's going to affect the graph. We're going to be introduced to a new idea. We've talked about the derivative in the previous section. We're now going to talk about the second derivative. Because the original derivative is still a function of x, we can still refer to it, and we can still take the derivative of it again a second time. So if we look at the graph here, let's talk about concave up and concave down, which has to do with the second derivative. We'll make that connection here in just a few minutes. But what we mean by concave up is when we have the graph, you can see the part A there. The graph is concave up because it's sort of like if light were to come bounce off that, it would bounce up. And concave down would be the opposite. It's facing downward. And the figure below, we can see that this figure has some places where it's concave up, some places where it's concave down. And our second derivative is really going to highlight for us the points where it changes from concave up to concave down and vice versa. That's going to be sort of one of its big purposes here. So the derivative of function f is a function that gives information about the slope of f. The derivative tells the original function is increasing or decreasing. So when we take the first derivative of our function, if the slope is positive of the slope of the tangent line, which is what the derivative function is, if it's positive, then it's increasing. If it's negative, then it's decreasing. It says because f is a function, we can take its derivative. This second derivative also gives us information about our original function f. Second derivative tells the original function whether it's concave up or down. And here is our second derivative test. So here we have y is a function of x. The second derivative of f is the derivative of the derivative. And we used a prime notation. It's f double prime or y double prime. And with Leibniz, Leibniz looks a little weird. I'll give you that. There's a reason that it's written this way. Well, I won't get into it, but this is the notation. So all this means, if you see this, is take the second derivative. If double prime is positive on an interval, then the graph is concave up. And if the second derivative is negative, then it's concave down. This is not right. Hang on. Positive, then it's concave up. This one should be concave down. Down. I'm looking at my wife's notes, and she also scratched out up and wrote down. Okay, so that was just a typo. So please make sure you correct that in the notes. We say it's increasing. Okay. If f of x represents the position of particle at time x, then v of x is the derivative. And so that's the velocity function. And the derivative of the derivative, or the derivative of the velocity function, is the acceleration function. We don't focus too much on that in this class. If this was a classical calculus class, then we would. All right, and so we are going to be given a function. F of x is our position function. 5x cubed plus 4t, 5t cubed plus 4t plus 9. And we're going to give the velocity function in terms of time. So that's going to be the 15t squared plus 4. And at 3 seconds, so v of 3 is going to be 15 times 3 squared plus 4. And so I am getting, let's see, 15 times 9 plus 4. So we're getting 139 meters per second. And the acceleration is going to be the second derivative. So the derivative of the velocity function is the acceleration function. And looking up at part A, that's going to be 30t. And the acceleration at 3 seconds is going to be 30 times 3, which is 90 meters per second squared. see our answers. Velocity function, and then a specific value, and acceleration function with an acceleration value. All right, oh, we're still in velocity. I thought we'd be more business focused, but that's okay. So we have another function, a position function, which is 4t cubed plus 12t squared minus 36t. And this is the motion of a particle. Find the function for the velocity. So again, that's just the first derivative. 12t squared plus 24t minus 36. And where does the velocity equal 0? That's going to be 12t squared plus 24t minus 36 equals 0. And I'm actually going to divide through by 12 to keep it simple. Oops. So t squared plus 2t minus 3 equals 0. So we are here. So t is going to be -3 and 1. And this is, it doesn't give a unit. I'm assuming that's in seconds, but I could be wrong. So -3 and t at 1. Now it says hint factor out the greatest common factor. That just, what I did was instead of factoring out the 12, I divided through by the 12 because we're going to set it equal to 0. And the acceleration function is going to be 24t. So I'm taking the velocity function up there and taking its derivative with respect to t. So these are our answers. All right, so let's talk inflection points. I've actually pointed out the inflection points before. An inflection point is a point on the graph of the function where the concavity of the function changes. So I pointed those out way up here. So that's the purple. Those are the inflection points. So it's changing from concave up to concave down or concave down to concave up. Working definition, inflection point is a point on the graph where the second derivative changes sign. Okay. And we can see here, I will overemphasize the red. So here is an inflection point, and here is an inflection point. E does not count. Notice it goes from concave down to concave down. E is a problem. In fact, we would even say that at E, f prime of x does not exist. So the only two inflection points that we see here is point B and point G. All right, so we have a graph, and it says at the point shown on the function above, which of the following is true? Sorry about that. All right. So the point here, we are in concave up, where that point is. So we are at f double prime is positive in this case. Also, the tangent line, I'm going to notice the slope of the tangent line is a positive slope. So the first derivative is positive. The second derivative is also positive. That is going to give us this one here. Slope of the tangent line is positive. So that means the first derivative is positive. And it's concave up, which means the second derivative is also positive. And as we're looking at this last graph here for this section, it says the function graphed above is decreasing on the interval. So it's decreasing from -3. So from here, -3, up until about 1/2. And the inflection point is somewhere in here. I'm gonna say about right there. And meaning it's going from concave downward to concave upward there. And that X value, ooh, is a squishy, I'll say -1.25. So it's hard to tell since it's not right on it, but we can make a good estimate. Yeah, so that's the second derivative in concave up. And the next section is optimization, which is a big one. I'll see you then.